Let me just, yeah, and let me go to presenter view. All right. Can you all see this slides? Great, wonderful. So yeah, thanks again, Sahar, for hosting and for the introduction. My name is Yana Kashtan. I'm going to be sharing the results of one project that I helped work on, measuring benzene emissions from gas and propane stoves indoors. Not did not work alone. There are lots of folks who helped with this. Some of whom are on this call. Certainly, I saw Meta and Rob. So thanks so much. I'm just going to give a little bit of background first on gas stoves and why we care about them particularly. Share a little bit of the methods and sampling scheme where we went to look at these emission rates, what we actually found from the stoves, and then a little bit of context on health and sort of what the concentrations we found mean for human health. So just a bit of background before I get into this particular study. I apologize if some of this is old news to a lot of the folks on this call, but I think it is important to take a step back and ask, why stoves? Why gas stoves? After all, they consume less than 1% of US natural gas. So they're, in that sense, peas in the ocean. But they are important to study for a few reasons. First of all, they tend to be unvented. While a lot of people have range hoods, a lot of people don't have any range hoods, especially outside of California. Many range hoods recirculate. And even for outside venting range hoods, we know from other research, including work of Brett Singer, that hoods aren't always effective at removing all the pollution. And that's in contrast with furnaces and water heaters, which, if working properly, are all vented to the outdoors. And so the pollution does not build up inside if they're working properly. Stoves are also widely used. Over a third of US households have gas stoves. And that's true for many countries worldwide, like Australia. I also think of stoves kind of as a gateway to gas. People have emotional attachments to stoves more so than other appliances. So if you are thinking about building new construction and are worried about customers insisting on, or potential buyers insisting on a gas stove, you might put that extra capital expense up to build gas infrastructure that then makes it easier to use gas furnaces and water heaters that end up consuming the majority of gas. So that's sort of another reason that stoves are sort of particularly important to look at. So what do we know so far about emissions from gas stoves? Prior work shows us that burning gas in stoves produces carbon monoxide, formaldehyde, and nitrogen dioxide, all hazardous air pollutants. And from the point of view of health, we're most concerned about the nitrogen dioxide just because of the ratio of concentrations that are observed to health benchmarks. So previous work has shown, including work led by Eric Lebel, well known here, has shown that regular use of a gas stove can elevate indoor NO2 concentrations above the EPA's 1 hour health benchmark. And that translates into concrete health outcomes. So various meta-analyses have estimated the odds of developing pediatric asthma if you grew up in a house with gas stoves as being elevated by 20 to 40%. And that in turn translates to a population attributable fraction of childhood asthma in the US of between 6 and 20%, meaning between 6 and 20% of US childhood asthma can be attributed to gas stoves. So that's sort of where we're at now. And we were curious to dig a little bit deeper and a little bit of background on the chemistry and motivating some of our questions here. The product of a gas flame, I like to sort of, in my head, I split them into 3 categories. So there's the nitrogen dioxide and nitric oxide, NO2 and NO, which are just produced because you've got O2 in the air and you've got N2 in the air, and in the high temperature of the flame, they will combine or can combine to form NO2 and NO. Then there is CO2, which happens when you completely burn the methane fully and you get CO2. Okay. And then there's a whole panoply of compounds that are basically partially oxidized between methane and CO2, some of which are toxic, some of which are not. And two of those are CO and formaldehyde, both of which we know come from, are emitted by gas stoves. And so our question was, okay, what else might be emitted? Are there other potentially hazardous compounds in this partial combustion category that are emitted by gas stoves? And so we set out to see, what other combustion products might be emitted, and if there are, how much is emitted? How do the emissions from gas stoves compare to the electric alternatives and to the food itself being cooked? And then, okay, given an emission rate, what actual concentrations might people be exposed to under realistic conditions? And we zeroed in on benzene because benzene is already known to be produced in methane flames from previous laboratory studies in much more controlled settings. And so it seemed like it was a reasonable hypothesis that it would be also emitted from methane flames in stoves. And also, of all the partial combustion products, benzene is enormously toxic. It's a proven human carcinogen and is carcinogenic at very low levels of exposure. So we thought it was particularly important to know whether stoves would be emitting this. Another sort of more pedestrian reason is we had an analyzer that was able to measure benzene. So a little bit about how we actually went about this. This will be familiar to those of you familiar with Eric Lebel's work on emissions of methane and NO2 from gas stoves. We used a similar strategy to look at benzene. So to look at emission rates, again, this is not concentrations under realistic conditions, but just to look at the emission rates of benzene, we essentially converted each kitchen to a laboratory chamber. So we would reduce air exchange between the kitchen chamber and outside the outdoors and between other rooms by sealing off open areas with plastic, and then homogenizing the air using fans so that the air was well mixed. And then, after correcting for air exchange, the calculation of emission rate is fairly simple. It's the change in concentration of benzene times the volume of the chamber divided by time. Now, we measure the concentration of benzene using this sampling hose, which is attached to a pump that draws kitchen air out to analyzers outside. And we measure the volume. We've done both using mechanical measurement, laser measurement, and also using a tracer gas. And we also use the tracer gas to measure the air exchange and then to correct for it. You'll notice a pot here on the stove, and we use that just because we want to mimic a real world situation of having a pot on top of a burner. And then we just boil water. And we verified that boiling that water doesn't emit any detectable benzene, which is to be expected. So that's sort of the kitchen picture. The air from the kitchen is pulled out and then goes to our sort of mobile field setup. I'm highlighting this here. We've got Zutao and Colin working on the aroma. I want to highlight this green aroma VOC analyzer because this enabled our work. It is a cavity ring down analyzer that is able to measure sub-part per billion benzene concentrations and is light enough and small enough to fit in the back of the car and to enable these mobile measurements that, previously you'd need a very large GC and much worse time resolution, and you'd have much worse time resolution. So definitely highlighting that as something, a key piece of instrumentation that enabled this work. And with its, given that it's mobile, we thought we should look at some geographic variability. We sampled throughout the San Francisco Bay Area. We also went to Southern California, to Bakersfield and to Los Angeles, and in Colorado around Boulder and Denver. And there's two main reasons for looking at this geographic variability or sampling in different geographies. First is that we know that the composition of the actual raw gas itself differs significantly in different places. Obviously, the majority of it is methane, but the amount of different trace compounds differs. Now, we didn't particularly expect that this would affect the combustion products, but we thought it was worth checking. And the other reason is that the building environment, everything surrounding the stove, can vary significantly in different places. People have different houses. The housing stock, sorry, I've got a cat that wants attention. The housing stock is, different ages. And so what people are actually exposed to can be different. So what did we find? Sorry, just gotta. So what do we find? What we found is that gas and propane stoves emit benzene about 10 to 25 times more than electric coils. And emissions of benzene from induction stoves were undetectable. That you can see here, I'm showing for burners on high. Similar results, though, we had for ovens and for burners on low. The other thing to notice, too, is that the emissions are long-tailed. So you can see there are a few really high emitters, and then also quite a few more moderate emitters. I'm just going to anticipate one question here, which is, wait, electric coils emit benzene? Our hypothesis for this is that little bits of oil and food getting on that 500 or 600 Celsius red hot coil do burn and do emit tiny amounts of benzene. But as you can see, much less than the gas or propane. I'm going to move on to concentrations in a moment, but first I want to revisit sort of our motivator for looking at benzene in the first place, which was the observation that stoves emit carbon monoxide, which is a partial combustion product. So a follow-up question would be, okay, do the conditions that produce carbon monoxide in stoves also predict benzene emissions? So plotting carbon monoxide emissions against benzene emissions, we do find a correlation. Carbon monoxide emissions don't explain all the benzene emissions, but they do explain a good bit, and suggest that there's some underlying condition of incomplete combustion that is causing both emissions. Okay, so we've seen that the gas and propane stoves emit benzene significantly more than their electric counterparts. But that's not quite enough to really see is this something really worth digging into more, because after all, what matters is the concentrations people are breathing in, right? The dose makes the poison in a way. I want to stress the main goal of this work was getting emission rates, which are key to, sort of the key bedrock for any kind of indoor air concentration modeling and are really important to get right. And so most of our time sampling was getting emission rates. But we did want to have a sense of whether the emission rates we were measuring may translate into concentrations that are potentially consequential for health. And so we did a few sort of case studies. One was, okay, what happens if we open all the interior doors, so no plastic, no tenting, no fans. We sort of mimic a scenario of like baking bread. You've got the oven on for an hour and a half, and measure the concentrations over 8 hours in the bedroom, in the farthest bedroom from the kitchen. What concentrations do we observe? And what do we observe, for relatively low emitting ovens and high emitting ovens? So here's just one particular house that we measured. You can see basically the bedroom is down the hall here to the left. And so what we found is, for really high emitting ovens, in the bedroom, we found concentrations that exceeded not only the California 8-hour reference exposure level, but even the California acute reference exposure level, which translates to about an hour-long exposure. For more moderate emissions, we found it exceeding the 8-hour reference exposure level for several hours, with a time average concentration that's remained above the 8-hour reference exposure level. And for ovens that emitted below the median, still elevated benzene even in the bedroom, but staying below that 8-hour reference exposure level. So that was sort of a range. And here we put I'll get more into this later, but here we have some international exposure standards from different countries, and comparing them to what we saw in the bedroom. So that was sort of looking at, okay, benzene emissions moving throughout the house, and what kinds of concentrations do we see? We only were able to do 6 bedrooms because, as you can see, it's a very labor-intensive measurement, 8 hours. So a bit quicker. We also got individual data points in untented kitchens. Again, no plastic here. Following 45 minutes with either one burner on high or one oven at 350 Fahrenheit. And what we found is that in all but 2 cases, the benzene concentration was elevated above baseline. And that in about a third of the cases, we had benzene concentrations that exceeded 0.8 parts per billion, which is the upper estimate of what you'd have in a house with a smoker. So sort of the concentration of benzene in secondhand smoke. Notably, this is also about a third of cases above that California 8-hour reference exposure level. So this was certainly, I think, enough for us to say, hey, these emission rates that we're measuring certainly can translate to consequential increases in benzene concentrations, and certainly worth doing maybe a more systematic look. But we also wanted to contextualize our emission rates in another dimension, which is, okay, we've compared the emission rates between gas and electric, and we've seen, okay, what happens, how do these emission rates translate into concentrations you're actually breathing in, or can, at least in some cases. But of course, cooking also involves food. So what about the food itself? After all, if the food emitted way more benzene than the gas, then, well, you should go with the low-hanging fruit first. You should focus on that first. So we wanted to answer that question. So there's no good data as far as we know, sort of systematically looking at benzene emissions from the food itself, from the food alone. But benzene is a partial combustion product, and ultrafine particles also are partial combustion products. So we looked at a California Air Resources Board report that looked at particulate emissions from food. And we picked the two meals there that emitted the most particulate, sort of as the worst case scenario. So frying bacon and frying fish in olive oil. And we cooked both of those meals on an induction cooktop that we knew had zero benzene emissions. And as you can see from this plot here, also observed zero emissions from the food itself. Of course, this is just two meals, so I want to be careful with making this overly broad, but at least when it comes to these two meals, which we believe are worst cases, the benzene comes from the gas or the propane, not from the food. So that's sort of our findings in a nutshell. I want to take a couple of slides just to contextualize them a little bit more. I mentioned the California reference exposure levels and a couple of other countries' benchmarks. But here is sort of a more global picture of what different countries have adopted as their benzene exposure levels. Mind you, these are not occupational exposure levels, but these are sort of levels deemed appropriate for the whole population, including vulnerable groups. The WHO, noting that benzene is a carcinogen, says because it's a pretty linear dose response curve with no lower threshold below which no effects have been found, they say no safe level of exposure can be recommended. But they also say, okay, if you're exposed to 0.5 part per billion of benzene over the course of your lifetime, then your risk of developing leukemia is 1 in 100,000 elevated. And that's a common benchmark that is adopted. So one in 100,000, which translates to 0.5 part per billion. And that is reflected in some country standards. So you can see Sweden and France have exposure levels around that level. Most of the national standards fall somewhere between 1 and 1.6 part per billion. So for context, we measured concentrations between 0.8 and 6 part per billion in about a third of the kitchens that we measured. And we didn't, a priori select the kitchens. These were just, as far as we know, a random sample of kitchens. So certainly this is something I think that deserves more work and is potentially of concern. Another way to contextualize this is, instead of looking at sort of international benchmarks, like what happens here in the US when these concentrations are measured outdoors. So just two sort of examples, one in California and one in Colorado, both states that we measured. When outdoor air monitors detected concentrations between 8 and 15 parts per billion, in both of these cases, there was local outcry. Local authorities immediately began investigating to find and stop the source. There was local news coverage. It was considered kind of a big deal. And I find this particularly important to point out because this is the upper end of what we actually measured in bedrooms. And this happens outdoors and it's a big deal, but it can happen in a bedroom and we don't even know. So again, I've been looking at sort of the benchmarks and the standards and people's reaction to these concentrations, all of which are based on medical literature looking at the actual effects on the body. So just a quick overview of what benzene actually does to the body. It's a very, very potent leukemigen and is associated both or is most potent at increasing the risk of childhood leukemia, mostly AML, acute myeloid leukemia. So in one cohort study of 4 part per billion benzene exposure over the course of childhood was associated with a 60 to 200% increase in childhood leukemia rates. And we have 2 different meta-analyses that look at benzene from traffic exposure and associate benzene from traffic pollution with higher childhood leukemia rates. I want to stress that these studies were unable to isolate the effect of benzene alone within all the pollutants that exist in traffic exhaust. However, benzene is by far the most potent leukemogene among them, and so I think this is still a worthwhile association to draw. So talked a bit about the health outcomes, and I also am aware that probably a lot of folks in this room are aware of a previous study that looked at benzene from stoves, and I want to make clear what that study found, what this study found, and what's different between the two. So our colleagues at PSE Healthy Energy, including Eric Lebel, looked at how much benzene is present in uncombusted gas. They combined this information with Eric's other work on known leakage rates of gas from stoves to calculate how much benzene was leaking from stoves just from leaks of uncombusted gas. In contrast, we actually measured how much benzene is produced when the gas burns. And we found that when you have the stove on and burning, it's emitting 70 to 640 times more benzene than when it's just off and leaking. So I don't mean to minimize benzene from leakage. Certainly, gas can leak in a lot of different places, not just the stove, but from as we know, from pipelines all throughout the distribution chain. So I think that it's really important to characterize benzene in the gas itself. But when it comes just to the kitchen and the stove, the source from combustion is much, much larger. So just wrapping up, and then I'll be happy to take any questions. Top line finding, again, the focus of our study was the emission rates. So 2.8 to 6.5 micrograms per minute of benzene when lit, when gas or propane stoves are lit. These can translate under some conditions into between 0.8 and 6 part per billion benzene in kitchens. This benzene can then travel into other rooms and doesn't seem to decay particularly rapidly absent active ventilation. And if you're looking at benzene from gas leakage versus benzene from combustion in a single stove, benzene emitted from combustion is by far the larger source of benzene. All right, thank you so much, and I'd love to take any questions.
Great.